Hey, welcome. So, have you ever looked up at the sky and wondered how we stay connected to a satellite that's tumbling through space? Or how we can possibly hear the faint whispers from a deep space probe millions of miles away? Well, a huge part of that magic comes down to this really elegant piece of engineering, the helical antenna. It might just look like a simple coil, but believe me, its design is a total masterclass in physics. So let's break it down and see how it really works from the ground up. Here's our game plan. We're going to follow the same path an engineer would. We'll start with the basics, then get into the nitty-gritty of its anatomy and the formulas. Then we'll see how one single angle, the pitch angle, changes absolutely everything. After that, we'll cover its two modes of operation, how the ground plane fine-tunes its performance, and finally, where you actually see these things out in the wild.
All right, first things first. Before we get into the how, we've got to understand the why. What makes this coiled wire so incredibly special?
So at its heart, a helical antenna is pretty simple. It's just a wire wound into a coil sitting on top of a ground plane. But its real genius comes down to two superstar properties. First, it's a broadband antenna, which just means it works really well over a whole bunch of frequencies, not just one specific channel. And second, and this is the big one, it produces circular polarization. Now this is the absolute secret sauce for talking to satellites. See, with a normal signal, the antenna has to be lined up just right, but a circularly polarized wave is always spinning. That means it doesn't matter if the satellite is spinning or wobbling, you're going to maintain that link. It's brilliant.
Okay, time to open up the engineer's toolkit. Let's really get our hands dirty and break down the physical parts and the core formulas you need to actually design one of these. The anatomy itself is pretty straightforward. You've got the helical conductor, that's the coil doing all the work. It gets hooked up to a coaxial feed. Then there's the ground plane, which acts kind of like a backstop or a reflector. Now for an engineer, it all boils down to two main variables you can play with. D, the diameter of that coil, and S, the spacing between each turn. Those are the knobs you get to tune.
And this is where things get really clever. To figure out the math, imagine we just take one single turn of that coil and we unroll it flat. And what do you get? A simple right-angle triangle. It's that easy. The bottom of the triangle is just the circumference, c, which is pi times the diameter. The height is the spacing, s. And the hypotenuse, L0, well, that's the actual length of the wire for that one turn. And just like that, with some basic high school trig, we get our key design formulas. We can find the wire length with Pythagoras, and we can define that all-important pitch angle, alpha. As you're about to see, that one angle is the key to this whole thing. Okay, let's zoom in on that pitch angle alpha. This isn't just some random number in a formula. This is the decision. It's the one choice that literally determines what kind of antenna you are building.
This flowchart here tells the whole story. Let's look at one extreme. If you set that pitch angle, alpha, to 0 degrees, what happens? Well, the spacing S becomes 0. The turns are all squished together, right on top of each other. And at that point, you haven't built a helical antenna, you've actually just made a multi-turn loop antenna. Totally different beast.
Now let's go to the other extreme. What if you make alpha a full 90 degrees? Well, the spacing S basically becomes infinite. You've stretched that coil out so far that it's just a straight wire pointing up. And what you've got then is a simple linear monopole antenna.
So, you see, the real magic happens right here in the middle. It's only when that pitch angle is somewhere between 0 and 90 degrees that you get that perfect spacing and you create the classic honest-to-goodness helical antenna. The form really does follow function, and it's all dictated by this one angle.
Okay, so we've nailed down the physical shape. But how does this thing actually behave when you pump a signal through it? Well, a helical antenna can act in two completely different ways, or modes, and it all depends on how big the antenna is compared to the wavelength of the signal.
So over on the left, we have what's called normal mode. This is what happens when the antenna's dimensions, the diameter and spacing, are really small compared to the wavelength. We call this electrically small. And in this mode, the antenna radiates out to the sides, perpendicular to its main axis. You get this kind of broad, donut-shaped radiation pattern. But this, on the right, this is where the real power is. This is axial mode. This mode kicks in when the circumference of the helix is roughly the same size as the wavelength. And when that happens, something amazing occurs. Instead of radiating to the sides, it fires a super-focused, high-gain beam straight out the end, right along the axis. It's like a spotlight.
And really, that's the main takeaway here. Sure, normal mode exists, but it's that incredibly focused, long-range beam of axial mode that makes the helical antenna such a powerhouse. This is the mode engineers are almost always shooting for when they design these things.
So we've got our shape, and we've picked our mode, but there's one more piece to this puzzle, the ground plane. Now don't think of it as just a boring piece of metal to mount the antenna on. No, it's an active player in the game, and it helps shape the antenna's performance. The ground plane is doing two really important jobs. First, it provides some stability and protects the delicate feed point where the cable connects. But more importantly, it acts like a reflector. Think of the reflector behind the bulb in a flashlight. It takes all the light going backward and bounces it forward into one useful beam. The ground plane does the exact same thing with radio waves. And you can even level it up by shaping it into a cup or a cone to get even better performance.
Okay, if you're an engineer, you're going to want to write this one down. This is a critical rule of thumb. For that ground plane to work right, to be an effective reflector, its diameter has to be at least 3/4 of the wavelength you're using. If you make it too small, energy just leaks around the back, and you lose all that forward gain you were working so hard to get.
We've gone through the whole design path, from the basic geometry all the way to fine-tuning its performance. So, where does the rubber meet the road? Let's check out where these antennas are actually put to work. Their special skills make them perfect for some really tough jobs. Remember that circular polarization we talked about? That's non-negotiable for satellite and space comms. That high-gain spotlight beam from Axial mode, that's exactly what you need for telemetry and radio astronomy, so you can pick up those incredibly weak signals from deep space. And even in RFID systems, that circular polarization is a game changer, because it means you can read tags no matter which way they're facing.
All right, let's tie this all together. We're going to do a quick flyby of the entire design path we just walked through, from start to finish.
It's such a logical process when you see it all laid out. It all starts with the physical geometry, your diameter and spacing. That choice sets your pitch angle. The pitch angle then defines the antenna's fundamental form. Is it a loop, a monopole, or a true helix? Then the size of that form compared to the wavelength dictates its electrical behavior. Are you in normal mode or axial mode? And finally, you polish it off and maximize your performance with a properly sized ground plane. See? A beautiful, logical flow from a simple idea to a real-world antenna.
So there you have it, the complete engineering blueprint. We've gone from a simple coil of wire to a high-performance antenna that can reach across the entire solar system. It's pretty incredible stuff. So the only question left is, now that you know how it works, what problem would you solve with it first? Let us know what you think.